In this lecture, we will draw the output or drain characteristics of N-channel JFET. We will draw the output or drain characteristics of N-channel JFET. If you remember the output characteristics of common emitter transistor, we obtained various IC versus VCE curves. We obtained various IC versus VCE curves where IC is the output current, or the collector current, and VCE is the output voltage or collector to emitter voltage. And these curves we obtained for different base currents IB, where IB is the input current. So this was the scenario in case of common emitter transistor. Now in case of junction field effect transistor, whether N channel or P channel, we obtain the curves between current ID and voltage VDS, where ID is the drain current or the output current, and voltage VDS is drain to source voltage or the output voltage. And we obtain these characteristics for different levels of voltage VGS, where VGS is gate to source voltage or the input voltage. In case of common emitter transistor, current IC is dependent on the base current IB. So we can say that base current IB is the controlling current, and in case of JFET, current ID, which is the output current, is dependent on the voltage VGS. VGS is the input voltage and it is the controlling voltage. The controlling voltage is different in case of N-channel JFET and in case of P-channel JFET. In case of N-channel JFET, controlling voltage VGS is negative. VGS is less than 0 volt. This means gate terminal is at the lower potential as compared to the source terminal. In case of P-channel JFET, VGS controlling voltage is positive. This means gate terminal is set at the higher potential as compared to the source terminal. Now we will plot the output characteristics, and for this we will first draw the x-axis and the y-axis. The x-axis is for the independent quantity, which is VDS in volts. The y-axis is for the dependent quantity, which is the drain current ID in milliamps. This is the origin, and with JFET there comes the values of IDSS, and the pinch of voltage. IDSS is the maximum drain current, and the condition to obtain IDSS is VGS equal to 0 volt and VDS greater than mod of VP. This is the condition to obtain the maximum drain current IDSS, and for this particular case, let's say IDSS is equal to 8 milliamps. VP is the pinch of voltage, and let's say it is equal to -4 volts. So we are obtaining the output characteristics of N-channel JFET with IDSS equal to 8 milliamps and VP equal to -4 volts. Now first we will obtain the curve when VGS is equal to 0 volt and VDS is some positive voltage, and after that we have to increase VDS to obtain the curve. Initially VDS is equal to 0 volt, and when VDS is equal to 0 volt, ID is equal to 0 amp, because across the N channel the potential difference is equal to 0 volt. So electrons will not be drifted towards the drain terminal and there will be no conventional current ID. So initially when VDS is equal to 0, ID is also equal to 0. Now on increasing VDS, ID will increase linearly. ID will increase linearly like this. If you increase VDS, the depletion region will also increase, and after some time it will appear that the two depletion regions are touching each other. And when this happens, the corresponding VDS is called as pinch off voltage VP, and the drain current ID will become constant because the channel will become very narrow, and if you increase VDS further, IDS will not increase, it will remain constant. Let's say the x coordinate of this point is the pinch off voltage. If I drop a vertical line on the x-axis, it will give us the pinch off voltage. This voltage is the pinch off voltage. I will represent it by VP. And now if you increase VDS, current ID will become constant like this. So this is how you have to obtain the curve when VGS is equal to 0 volt. I will write it here. VGS is equal to 0 volt, and this current is the maximum drain current IDSS. The given pinch off voltage is for the case when VGS is equal to 0 volt. So this pinch off voltage here is equal to 4 volts. Now we will consider the case number 2. In case number 2, VGS is negative. Let's say it is equal to -1 volt. In case number 3, we will make VGS more negative, equal to -2 volt. In the case number 4, we will make it -3 volts, and in the last case we will make it -4 volts. So these are the next 4 cases, and at this point I will give you one homework problem. You can see we are making VGS more and more negative. Why we are not making VGS positive? You have to tell me the effect when we make VGS more positive for n-channel JFET. Once you have your answer, post it in comment section. And now we will discuss the case number 1. When VGS is less than 0 volt, it is negative, and VDS is positive, greater than 0 volt, n-channel is connected to the positive potential and p-type materials are connected to the negative potential. I will write this down. N-channel is connected to the positive potential and p-type materials are connected to the negative potential. And this is the case of reverse biasing. The PN junction is reverse biased in this case. Now if you make VGS more and more negative, this means you are applying more negative potential to the p-type material, and this will increase the reverse biasing. So the things are very clear. If you make VGS more and more negative, the negative potential applied to the p-type material will increase, and hence the reverse biasing. And when reverse biasing increases, this implies the width of depletion layer will also increase. So making VGS more and more negative will increase depletion region, and when depletion region increases, the pinch off we can achieve at the lower value of VDS. Because when the two depletion regions appear to touch each other, the condition is called as pinch off voltage, and making VGS more and more negative helping us to achieve the pinch off earlier. So when we make VGS more negative, it is -1 volt. In the case number 2, initially it was 0 volt. So we are making VGS more negative, and because of this reason we will have the pinch off voltage at the lower value of VDS. So let's see how the plot will look in case number 2. Initially when VDS is equal to 0, ID is also equal to 0. After that it will increase linearly like this. But the pinch of voltage we will have early. The x coordinate of this point is the pinch of voltage in case number 2, and if you increase VDS more, the drain current will become constant like this. So this curve is for VGS equal to minus 1 volt. In the same way, when you make VGS equal to minus 2 volt, you will have the plot like this. This is for VGS equal to minus 2 volt. For VGS equal to minus 3 volt, again we will get the pinch of voltage early as compared to the earlier case, which is VGS equal to minus 2. And for the last case, when VGS is equal to minus 4, you can see it is equal to the pinch of voltage VP. So when you have VGS equal to the pinch of voltage, there is no need to apply VDS. When VDS is equal to 0, when the potential difference across the N channel is equal to 0, in that case also the two depletion regions will touch each other. And if you increase VDS, the current will not increase. So initially the current is equal to 0, and if you increase VDS more, the current will still remain equal to 0 amps. This is for VGS equal to minus 4 volt, which is equal to the pinch of voltage VP. So this is how you have to plot the characteristics, the output or drain characteristics of the N channel JFET. In case of P channel JFET, instead of making VGS more and more negative, we have to make it more and more positive. Now I will draw the locus of pinch of voltages. This is the first pinch of voltage, this is the second, this one is the third, the fourth, and this is the fifth pinch of voltage. And if you join these points, you will have the locus of pinch of voltages. This one is the locus of pinch of voltages. Now I will explain different regions in this output characteristics. This region here, this region is the ohmic region. We are calling it ohmic region. This region we are calling ohmic region because you can see current ID and VDS are having linear relationship. ID is directly proportional to VDS, and this is the condition of Ohm's law. So our N channel JFET is acting as a linear device in this region, so we are calling this region ohmic region. The region is starting from the point when ID becomes constant and remains constant is called as the saturation region or pinch off region or the active region. I will show you the active region. This region is the active region. We also call it pinch off region or the saturation region. When VGS is equal to the pinch off voltage, ID is equal to 0 amps, and the VGS required to make ID equal to 0 amps is called as gate source cutoff voltage, and for all the practical purposes the device has been turned off. So this region here is the cutoff region. Now we will talk about breakdown region. If you go on increasing VDS, like any semiconductor device, there will be breakdown. The electrons will gain the kinetic energy and high drain current ID will flow through the device. So if you go on increasing VDS, breakdown of the device will occur and the drain current will increase drastically like this. So this is how the curve will look in breakdown region. A very high drain current will flow through the device. So the last region, the fourth region, is the breakdown region. So this is all for this lecture, and don't forget to solve the homework problem. You have to tell me the effect on making VGS more and more positive on N channel JFET and channel JFET. Once you have your answer, post it in comment section. I will end this lecture here. See you in the next one.